Okay, in the previous video what we had discussed was recursively constructed rearrangeably non-blocking switch as well as structurally non-blocking switches, and as a consequence what will be the cross point complexity. Okay. So, and then of course we have estimated that we could improve my cross point complexity from O(n) square, which was for a crossbar. Using a closed network I was able to come to 3 by 2. By doing a recursive construction I was able to come to log 2n 2.58. Okay. While for rearrangeably non-blocking switch we actually came up with a cross point complexity of this. Of course, I had already mentioned that while coming from here to here, this was actually strictly non-blocking n by n crossbar for unicasting as well as multicasting scenarios. Any arbitrary multicasting scenario can actually be handled here. But when we came to this closed network, this was not for arbitrary multicasting, was not supported for this one. I have not actually given you the cross point complexity when the multicasting will be F-way multicasting will be taken care of. So, if F is become equal to R3, which is number of switches in third stage, then it become an arbitrary multicasting actually can be supported. So, we have not computed the cross point complexity of that, but if we use a closed network for unicasting, coming from here to here I actually lose the strictly non-blocking nature for multicasting, but retain it for unicasting and my cross point complexity reduces. If I do recursive construction I can actually further reduce it. Okay. So, and this was done for the rearrangeably non-blocking switch. Now, we would like to figure out if we can further improve on this particular bound. Can I further go down? So, this question was also is still actually prevalent, we still do not know what is the bound. It is going to be worse than this, but we do not know how much. So, it has to be somewhere between these two. So, Cantor actually discussed this particular issue and he came up with something called Cantor network, and he computed that he can build up a strictly non-blocking switch in this configuration, and cross point complexity for this after he has estimated everything was log 2n raised to power 2. So, from 2.58 I was able to come to 2. Okay. From 2.58 I was able to come to 2. We still do not know whether we can further improve it, whether it is going to be O(n) log 2n 1.75 or so, we do not have the answer. So, we will leave with this particular bound and then we will move to our next video on wide sense non-blocking system. So, how the Cantor network will look like? So, once I actually today what I am discussing is the Cantor network topology, and we will be estimating what is going to be the cross point complexity for that scenario. So, cross point network, this Cantor network will look something like this. I have already told you the structure of a Bayes network. So, for 8 by 8 for example, I am drawing a 8 by 8 Cantor network, I have to draw the Bayes network here. So, Bayes network will look something like this. It should have 5 stages. And this will be the connections. So, I think all of you can recall this. So, this is 8 by 8 Bayes, and we know, as we have studied earlier in one of the videos, that this is a rearrangeably non-blocking switch. Okay, so, blocking will happen in this case. So, he actually Cantor came up with a very simple idea that let one input come in, I will use 1 by m switch, and I will use m such switching paths. So, this is the first one, first Bayes network, this is the second one, and this is the mth one. So, input 1 can be actually routed through this particular Bayes network. Since it is a blocking system, if it cannot, the a connection cannot be set up via this, it can be set up via 2. If this also you found that things are blocked, then it can go till m and so on. So, if I keep on increasing, and this actually means this is how it is connected. So, this is the mth connection. Okay. So, this is 1, 2 and their mth connection here. So, if I keep on expanding this on the similar on same lines, on the output side we will have something like this actually. There is an output and m lines from m different Bayes networks will be coming and will be put together. So, this output will be connected to any one of them. So, if I keep on increasing this m, this switch should become strictly non-blocking. So, question which is now is, at what value of m this will become strictly non-blocking. So, we will investigate this question now. So, in this case I have to draw other inputs because it is not one, there are actually n inputs. So, there is a nth thing. I can have the ith input also, let me put something intermediate so that I can show the connectivity. So, in this case it will be 8 by 8, so this will be value should be maximum should be 8. In general it can be n by n, then we will have n by n Bayes network which will be there, and of course we are assuming that n is equal to 2 raised power n. Okay. So, n is equal to this 2 raised power n is a small thing and n belongs to an integer, positive integer. Okay. So, I can call it a natural number set. So, n belongs to that and this is the size of n. In this diagram, because I have drawn 8 by 8 Bayes network, I will be having 8 inputs here. So, the first input in the ith switch, the first input will be always connected to the first switch and its ith input actually. So, if this is ith, which is in this case is 5th, so I should make it equal to 5 actually. So, this I will be connected to the 5th one. Okay. So, ith switch here gets connected to the ith input from this 5th input of this particular switch, because the number of this mux or demux is 5. Okay. So, similarly the mth here will be connected to the mth, in this case the ith input here will be connected to the mth input of this one. This logic will hold true for everything. Okay. So, this 2 will get connected here, this 2 will get connected here, and on similar kind of connections will be happening on the other side, on the output side. So, I will have 1 and this will be again I am taking some value, say I can call it k, this is the 8 which is equal to n in this case. So, if k can be here 3, so the third number line will come up and connect to the first one, from first switch. So, this will be 3. So, remember this port number corresponds to this input number, this port number corresponds to this switch number. On this same side also again this port number corresponds to this switch number and this port number corresponds to this switch number. Okay. So, this correspondence is always done so that you can symmetrically construct this particular switch. So, the last one will be coming here in this fashion, this last one will be coming here to the third one. So, this will be third one which will be coming, and this is the 2. So, that is what the Cantor network is. Now, only question which remains is what will be the value of m. So, now let us compute. So, we will do a very different thing this time. What I will try is, because let all the 7 other connections are already set up, and I have one free input and I have one free output which need to be connected. Okay. So, if what I will do is, I will try to find out to how many nodes in the first stage the free input can go, assuming all other connections have been made, and I will count not only these 4, I will count even these first stage also. There are first stage switches even sitting in here. So, I will count all these actually. So, in the first stage, in this case it is 32, 8 into 4 number of switches in the first stage which are present. So, how many of them one will be able to reach? One can actually reach, or whatever is a free port. So, let me assume it is 1, it is true for any one of the input port. If it is true for 1, it can reach 1 here, 1 here and 1 here. So, it can reach in total m, or is equal to 8. So, I define this number, I define AK as number of, and I call each one of them as a node. Okay, now, so number of nodes which are reachable in worst case in stage K. Okay. So, A1 in the first stage, what is the value of A1? Will be m. In this example, it will be 8. So, now now you can actually see all these 8 switches, this one, this, they now can actually be reached by 2 inputs, one, and if there would have been another one. So, let me draw it with a different color. It is there, I have not drawn it. So, 2 is somewhere sitting in between. So, let me just draw it for clarity. So, this 2 will also be connected to the same port, this 2 will also be connected to this same port. So, 1 and 2, so same switch. So, amazingly this one and 2 both are able to reach to the same set of nodes in the first stage. Okay. And since I am assuming that all other inputs are busy, so when you will try to look into the second stage how many nodes are reachable, so from this node it can reach to these 2, from this node again it can reach to these 2, from this node also again it can reach to these 2. Okay. But since 2 is already connected, it should be actually connected either with 1, 2, 3, 4 and 5, 6, one of these 6 actually ones. So, one is already occupied. So, number of nodes which are reachable in second stage will be, so A2, the number of nodes which are reachable, they should be twice the number, because each one of this switch is connected to 2 nodes in the next stage. Third stage it will be again 2 more, twice of whatever is reachable in the second stage. So, A2 should be equal to 2 into A1, but as I said that input 2 is already busy, so it is already connected. So, one of them has to be minused, has to be subtracted. So, the interfering one, the 2 has to be there. So, one node has to be made less. So, whatever nodes which are reachable by 1, A1, those can be further reaching to the third stage, and A3 will be twice of A2, but minus how much? Now, when I look at these 2 nodes, they are reachable from corresponding to third and fourth inputs also, and I am assuming they are also occupied. Similarly, these 2 can also be reached via these 2 ports, which corresponds to, of course, same third and fourth inputs. If they are already connected, it means 2 of these links which are going out from here, it is going to these, So, this one which I am now putting, so these are actually 1, 2, 3, 4 and these, so 4 into whatever is the 8 actually, whatever numbers which are there here m, 8 into m. So, those many switches are reachable now, but 2 of them will be occupied by these two third and fourth input. So, now it has to be 2 raised power 1. In general, if you take a larger switch, you will find that A of k. Now remember, I cannot go any further than the middle stage, only up till middle stage I can do. So, here only I can have A1, A2 and A3, I cannot compute for A4 here. So, I have to have a 16 by 16 switch to compute for A4 and 32 by 32 for computing A5 and so on. So, Ak will be now given as 2 a raised power k minus 1 minus 2 raised power k minus 2. Okay. So, you can actually see the relation. So, once you have got this relation of reachability, I am always interested in finding out in worst case scenario how many nodes I can reach in the middle stage from the free input 1. Okay. So, let us do that. We have to do a recursive computation. I can use this formula and then recursively compute, because I can now put a expression for Ak minus 1 using the same recursion and compute what is Ak in totality. Let us see. So, once I have Ak which is being given here, so what will be, I can actually now put Ak minus 1 expression. So, this will be using similar thing, it will be 2 into Ak minus 2 minus 2 raised power minus k minus 3 minus 2 raised power minus k minus 2. So, this comes here as this I have expanded into this, and if I solve it, it will be 2 square a k minus 2, this 2 will get multiplied here, it will become 2 into k raised power minus 2 . I can keep on doing it actually, and if I keep on doing it, I might actually get 2 cube a k minus 3 minus and so on once I reach to 2 raised power a1. So, here it has to be. So, remember this and this, when you sum together it will always come out to be k. So, it is 1. Okay. So, it has to be k minus 1. So, when you sum these two it will be equal to k. This is nothing but number of terms, which here it is 3, here it is 3, here it is k minus 1. So, I should have k minus 1 here, 2 raised power k minus 2. Okay, because this is a constant thing which will keep on coming, only this number will keep on increasing. So, k minus 1 time we will recurse, and this will be the final expression for Ak. A1, as we have already estimated, was nothing but equal to m. So, I can replace this by m, the total number of bins network which are there. Now, I am interested if it is, let us move to a general scenario. So, general scenario is for n by n switch. So, n by n Bayes network will be used, the middle stage will be log 2 of n. So, total number of stages in the Bayes network are log 2n, 2 log 2n minus 1. I am looking for the middle one, this is always a odd number, remember. Okay, log 2n stages, how many nodes I can reach, I am interested in that. So, let me do that, a log 2n. So, I have to just keep on putting the value of k and then keep on solving it. So, these are number of nodes which a free input 1 can actually reach. So, solving it, it will become 2 log 2n is n, because 2 to the power minus 1 will become 2, this will become m minus, same we will do, it will be n by 4. Okay. Now, the argument which we are going to have is that there is one free input. In the log 2n stage there are total lot of number of switches. Okay. Total number of switches which will be there in the middle stage will be nothing but each Bayes network will have n by 2 and there are such Bayes network which are present are m. So, total number of middle stage switches will be nm by 2. Now, the free nodes which I can reach from the free input will be some number, this is number is given by a of k, where k is log 2n. Same is true from the output side. So, I can reach certain free number. Now, if I add this number a k and the whatever I can reach, this will of course because of symmetry will turn out to be same expression. If these two numbers are added and if they are more than whatever is the middle number of switches which are available, then there is bound to be some common free node which is available. There has to be some node which is common between this set and I can always use that to route the call without disturbing the existing calls. Okay. So, in that scenario I have to just simply take 2a log 2n should be greater than nm by 2. This is the condition for strictly non-blocking operation of the Cantor network. So, once we take this I can put a log 2n from here, the above expression. So, this will turn out to be, let me write it on the left side, so it will be 2 times a log n, I am just putting, so nm by 2, 2 times of this minus log 2n minus 1 into n by 4, twice of this has to be greater than nm by 2. Okay. So, once I do this, this 2 will cancel with this and this will become 2. So, I can actually write it as this minus this will be nm by 2. This term I can take on that side, it will become positive. So, 2 cancels with this, n cancels with this, m has to be greater than log 2n minus 1. This actually implies that m has to be greater than or equal to log 2n. So, if m is satisfying this condition, the switch will be strictly non-blocking. Now, let us compute what will be the number of cross points which will be required in total for this particular switch. So, if you look, I actually used demux, this is a 1 by n switch, okay, because 1 by m actually, where m is log to n, and there are n such switches which are used, which are 1 by m switches. Then I actually had used Bain's network, which is n by n, and I had used m such Bain's network actually, and then there was a m by 1 switch, n such switches have been used. Now let us compute the cross points, total number of cross points which are required. This one require m cross points, there are n such elements, m into n will be there. Each Bain's network will require n by 2 switches are there, 2 stage switches in every stage, and 2 log 2 n minus 1 stages are there. So, n by 2 into 2 log 2 n minus 1, and each 2 by 2 will require 4 cross points, okay. And we have in total m such switches. So, I will put an m here plus, on the other side I have m by 1. So, you require m cross points and n such switches, so m into n. So, this is the total number of cross points which will be required. So, I can now put it 2 mn. This m also becomes log 2n. So, I can solve this one plus 2n. So, this will become 4n log 2n minus 2n, m becomes log 2n here. So, this will be this cancels with this. Your number of cross points which are required are 4n log 2n square, which implies my cross point complexity is On log 2n square, and which is a strictly non-blocking switch. Okay, so thus we have proved that we can improve the cross point bound which came from recursively built strictly non-blocking switch, and we can do better. So, that is what the Cantor network does.